We studied collisions in the last unit, right, on momentum. And we're going to use those concepts again. So I'm going to review momentum a little bit. And we'll review conservation of momentum during a collision. But then we want to talk about kinetic energy. And if it's lost, if kinetic energy is lost, we have an inelastic collision. And most collisions are at least a little bit inelastic. That is, some of the kinetic energy will be turned into the random motion of molecules, sound and heat and all that sort of thing will be given off. But some collisions, kinetic energy is not lost, which is an awkward way of saying conserved, and that's called elastic collisions. Okay, so let's do it. Well, first of all, remember what momentum is. We said that momentum, which we use the lowercase p for, who knows why, and it's a vector, and it's by definition equal to the mass times the velocity of an object. Well, let's take a look at when two objects collide. Here's object 1, here's object 2. This is before the collision. Maybe they're both moving, and they collide. So, bam, they smash into each other. So here they are smashing into each other. Here's 1 and 2. And object 1 and object 2 apply equal and opposite forces to each other. So here's the force of 1 on 2. Here's the force of 2 on 1. And of course, the force of 2 on 1 is equal but in the opposite direction to the force of 1 on 2. They're equal and opposite to each other. Which means if I look at this whole system, if I treat this as one system, there's no outside forces acting. We're going to isolate it. So we can say, well, oh, that means that F2 on 1 plus F1 on 2 is equal to 0. And here's another thing we can do. We can multiply this by time, this delta t. Delta t is the time it takes for this collision to happen. It's the amount of time that these forces are being applied to each other. And they're obviously being applied at the same time. So let's do that. F2 on 1 times delta t plus F1 on 2 delta t equals 0. We did this last time. Well, what is the net force? Look, this if this is an isolated system, this is the net force. This force of 2 on 1 is the net force on object 1, which is m1 times acceleration on 1, right? Net force equals mass times acceleration, but acceleration is delta v over delta t for object 1. And then we're multiplying that by delta t, right, from here. So this is force is mass times acceleration. Here's my acceleration, and that's going to, and the delta t is basically going to cancel out. And that gives mass times the change in velocity. Plus, same thing with m2. This is a force of 1 on 2. Is the change in velocity of object 2 over delta t, right? This is mass times acceleration, but we have this delta t that we decided to multiply by, and that equals, all equals 0. So here the delta t's cancel, and here I've got something quite interesting. The mass times the change in velocity. Well, we just defined momentum to be mass times velocity, so the mass times the change in velocity is a change in momentum. So this is the change in momentum of object 2. This is the change, object 1. This is the change in momentum of object 2. Now I'm skipping some steps here because for the interest of time. M1 times delta V1. Well, that's the change in momentum of object 1. Okay. Plus the change in momentum of object 2 is equal to 0. Okay, now I'm going to take this. I'll rewrite it up here because I've run out of room. Let me just rewrite it. Delta P1 plus delta P2 equals 0. This means there's no change in momentum in my system overall. What does delta P, what does delta mean? Anytime you have a delta, you have a change in, right? So this is a P1 final minus P1 initial. Does everybody agree that's delta P1 plus P2 final minus P2 initial? This is delta P2, and all of that's equal to 0. Now, what I'm going to do now is put leave the initial stuff over here, put the final stuff over on the other side, multiply everything by -1, okay, and what we get is P1 final plus P2 final, initial, doesn't really matter. It really doesn't matter which side you put things on. Initial equals P1 final plus P2 final. And what is this? Right here. This is the total initial momentum of my system. That's P initial. The total amount of momentum in my system equals P final. Because this is, so in other words, the total amount of momentum in my system doesn't change during a collision. Okay, so we just kind of reproved all that theory that we did a few weeks ago. Okay. Now this is true for all collisions. Okay. Momentum is always conserved in a collision. But what about energy? What about kinetic energy? Well, we have the initial kinetic energy of my system. K initial equals 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared. What? And so this is, and I can do the same thing for K final. Now, so K final equals the kinetic energy of the first object after the collision squared plus 1/2 the mass of the second object times its final velocity squared. So this is kind of messy. In some kinds of collisions, we don't lose any kinetic energy. Now we never lose momentum, but there are some collisions where we also don't lose kinetic energy, and those are called elastic collisions. In elastic collisions, these are the equations you use. P initial equals P final. You start there. You say, okay, what's moving before the collision? What's moving after the collision? Set their momentum equal to each other. But then, you also can add up all the kinetic energy before the collision, and it will be equal to all the kinetic energy after the collision. And that's called an elastic collision. They're very rare. It's very hard to make an elastic collision. You can come close. You have really good springs and everything. But even like billiard balls. Anybody here play pool? Okay. Now, billiard balls are very close to an elastic collision when they hit each other. But you do hear a sound, don't you, when the two balls hit? You hear that click sound when two billiard balls hit, which means they've lost a little bit of energy in that collision, which actually means that it's an elastic collision. But you can use these because it's so close that you can use this analysis. But then in an inelastic collision, well, first of all, P initial equals P final, doesn't it? It always does. But in an inelastic collision, you give off sound during the collision, or you dent the material, you make it warmer, you create internal energy, which is the vibration of, you increase the vibration of molecules after they hit. So not as much energy is left to be kinetic energy. So what's true about K initial versus K final? If you have an inelastic collision, you're going to take some kinetic energy away to warm up the material. Okay, next time you crash your car, okay? Let's say you crash your car. You drive it into a telephone pole because you were texting or something. And, okay, so here's what I want you to do. After the airbag kind of goes down, okay, get out of your car and feel the crumpled up hood. It'll feel a little bit warmer. In the deforming the metal, you've warmed that metal up. Okay, then call 911, But the first thing you should do is feel the heat that's being given off by the collision. Remember that we talked about the other day that comet that hit the Earth a long time ago and released all that kinetic energy? Released the kinetic energy was lost, actually, and it became heat. Or warmed up the environment. It vaporized all the rock. Now, in that collision between the asteroid and the Earth, or the comet and the Earth, momentum was conserved, but kinetic energy was lost. So the initial kinetic energy will be greater than the final kinetic energy. So that's the big difference between elastic collisions and inelastic collisions. In an elastic collision, you don't lose any kinetic energy. Where does this happen? Where do we have elastic collisions? When atoms collide, or like when galaxies collide, they interact gravitationally. There's very little, almost no heat. So, and usually what we have, almost virtually all collisions are a little bit inelastic, but they might be so close to being elastic that we can use these equations to solve the problem. But, by the way, solving these simultaneously is super hard to do. We actually do it in AP Physics. We're not going to do it in here. But I do want you to know, hey, what is your change in kinetic energy going to be? K final is going to be less than K initial, so what's true about delta K? What's delta K going to be equal to? Some number of joules, right? But it's going to be negative. Why negative? Because what is delta? It's the final minus the initial. So if initial is bigger than final, when you subtract them, you get a negative value. Make sense? And that negative means we're going to lose kinetic energy during that collision. So two kinds of collisions, elastic and inelastic. Most collisions are inelastic, which means we're going to lose kinetic energy during that collision. Elastic collision, the kinetic energy isn't lost. Okay. Let's take a look at the whole thing one last time. Okay, so we did a little review of momentum and what happens to momentum during a collision. And we basically go through all this mumbo-jumbo to come up with the idea that momentum is always conserved during a collision, but not necessarily kinetic energy. And those last three problems in Assignment 4, and that's why Assignment 4 isn't being checked today, involves elastic and inelastic collisions. Questions about that. So I wanted to explain that before I made it do. Okay, that is all.